Okay, so in this video, we're going to be talking about recursive definitions, and you can read about this in section 17.3 of the Logic and Proof book. So make sure that you go ahead and read that section before you listen to this video. So when I say a recursive definition, I'm talking about a definition of a function, and I'm sure you've seen a recursive definition before, I hope. But if you haven't, you shouldn't be very surprised about this. So roughly we can say a function f from, let's not say, normally I talk about f from x to y, but now I'm going to be talking about particularly a function defined from the natural numbers to any set y. We say that this guy is recursively defined if you define it in the following way. So if you first define f of 0, and then you define f of n plus 1 in terms of f of n. Okay, so first thing I want to say is that there are many variations of this, just like with induction. So you can maybe define f0 and f1 and then define f of n plus 1 in terms of f of n, or maybe you can change up 2, so number 2 of this kind of definition, so you could define f of n plus 1 in terms of f of n and f of n minus 1 or something. So there are many variations. This is just kind of the most basic kind of recursive definition. And I also want to say that this is closely related to induction. And like a lot of the stuff in this class, I always say, actually there's a way in which you can see recursive definitions and induction as being two instances of the same thing. That's a bit beyond this class, but they are somehow kind of the same thing. So it shouldn't be surprising that there are some similarities. So for example, for this first step, you define f of 0, whereas in induction, you want to prove p of 0. So they're very analogous there. And then here in the second step, in induction, you would prove p of n plus 1 from p of n. Here we're defining f of n plus 1 in terms of f of n. So it's very, very analogous to induction, and that's because you can see them as part of the same kind of thing. So here's an example that we're probably very familiar with. And this one isn't as basic as the formula that I've already given, but hopefully it won't be too crazy. So we're going to recall the formula for the Fibonacci numbers. And we're thinking of the Fibonacci numbers here as a function f from n to n. Okay, so it's a sequence. We normally think of it as a sequence, but a sequence of natural numbers you can think of as a function from n to n, where here f of 0 is the first guy in the sequence, f of 1 is the second guy in the sequence, f of 2 is the third guy in the sequence, and so on and so forth. So we're going to think of it as a function. So f of 0, we're going to let be 0, and f of 1, we're going to let be 1, and then f of n plus 2, we're going to let be f of n plus f of n plus 1. And this one we can say for all n in n. So if we're wondering what f of 0 is, well, it's right there in front of us, it's 0. If we're wondering what f of 2 is, then we have to think a bit more and look at this third part of the definition and say, okay, well, we should let n be 0 in that little line, and then we find that f of 2 equals f of 0 plus f of 1, and then we find that f of 2 is going to be 1. Okay, so that's how we can go through and write out all the Fibonacci numbers if we want to and if we have enough time. Okay, so that's a recursive definition of a function. The Fibonacci numbers are defined recursively. And because recursively defined functions They look so, I mean, the structure, like how they're defined, is so similar to how we do induction. They're kind of set up perfectly so that induction, proofs by induction work, um, or are the most natural way to prove things about recursively defined functions. So let's look at an example of a proof by induction. So we want to prove a fact about the Fibonacci numbers, which is that if we sum them up, so we sum up the first, all the guys from 0 to n, so it would be the first n plus 1 guys. Then we want to say that that's f of n plus 2 minus 1. And this should be true for all n. Okay, so we're going to do a proof by induction because that's exactly the right kind of thing whenever you're dealing with recursively defined functions. So we're going to proceed by induction on n. Okay, so for the base case, we need to show that this formula holds when we plug in 0 for n. So we need to show that this formula holds, this equation holds. So we should just do some calculations. So the left-hand side is just the sum of all the f's from 0 to 0. So that's just f of 0 by itself, summed up. And f of 0 is 0, so the left-hand side is 0. And the right-hand side, we just computed a few moments ago, that f of 2 equals 1. So the right-hand side is also 0. So we find that both sides are 0, so this holds, let's just say. Okay, so now we have to do the inductive step. So for the inductive step, we're going to assume that this formula holds. And then we want to show that the formula holds when we plug in n plus 1 for n. We need to show that this formula holds. F of n plus 1 plus 2 minus 1. Okay, so we're just going to do a calculation. A lot of these proofs by induction just really amount to calculation at some point. So we're going to calculate starting from the left-hand side. We're going to try to massage it into the right-hand side. So one nice thing with sums, I mean, kind of the reason why a lot of facts that you would prove by induction have to do with sums, is that you can easily separate out the sum here from 0 to n from the last guy in the summand, which is f of n plus 1. So now we know by our inductive hypothesis what this first guy is. This first guy is f of n plus 2 minus 1. And we can just write the rest of it down. So this is by the inductive hypothesis. We can say to let people know what's going on. And now we can just calculate. So we want to show the right-hand side of our desired equation here. Let me highlight this. So we want to show the right-hand side of this guy. So we want to show that our formula is equal to f of n plus 3 minus 1. But we know that f of n plus 2 plus f of n plus 1 is equal to f of n plus 3. That's the formula of f of n plus 3. So you would have to plug in here in this, this definition of f of n plus 3 up here at the top, n plus 1 everywhere that you see n. And then you'll find that f of n plus 3, or like f of n plus 1 plus 2, equals f of n plus 1 plus f of n plus 1 plus 1. So we know that f of n plus 3 equals f of n plus 2 plus f of n plus 1. That's the whole point. And we still have this -1 hanging out there. So we can say here, by the definition of f of n plus 3. Okay? And this is exactly what we wanted. We can maybe write it slightly more explicitly if we really want to, but it's probably not necessary. Okay, so we have this equation, long string of equations, I guess, that show that our equation that we're looking for is true. And now we can just sum up and say, thus, by the principle of induction, we find that this formula holds. Oops, not +1. This formula holds for all natural numbers.